I know, don't freak out. You said there wasn't any proofs in this unit. You don't have to do any proofs. This is just a proof that leads into the special right triangle because you guys know how to go in honors. I just don't give you stuff and say write it down. You have to discover it on your own. So that's what this proof is involving, discovering our new special right triangle. That's not 45, 45, 90. And it's not even that bad, so relax if you're going to start whining. I'm asking you to prove AD congruent to DC, and I'm giving you triangle ABC is equilateral and BD is a little altitude. Vocabulary term. All right, look, let's start. How are we going to show BD and AC? Or AD and DC congruent. We're going to have to do what first? Prove the triangles like usual. All right, help me out. Get me a pair of sides or angles that you know are congruent here. How else are you going to get AD and DC?
Equilateral is that all sides are congruent.
Yeah.
So wouldn't all angles be congruent? So, oh wait, never mind.
You good?
Yeah.
All right. Again, next time you have a thought, forget it. All right. Yeah, I didn't know how you were going to pull that off there. I was like, did I miss something, or did you think that was a median?
No, I thought it was the angles, and then I had two sides.
All right, we good?
Yeah,
Can I keep teaching again?
Yeah.
Thanks, I appreciate your permission. How about sides or angles that are congruent? Any sides or angles up here you want to start with if we're going to get these triangles congruent? All right, start us off right. We're going Matt. Here we go.
BD is congruent to BD.
Yeah, it is, Matt. Yep, that it is. The old reflexive. Always rely on that. Yep. All right, anything else here? Anything else? All right, let's go, Olivia. Anything else true? Yeah, yep. Angle BDA, BDC, they're right angles. Why, Olivia? Because I don't want perpendicular lines here. Yep, good. Definition of an altitude. Altitudes form right angles from a vertice. And then why don't we, while we're here, right after that, like we usually do, say those right angles are congruent. So angle BDA congruent to BDC. All right angles congruent. All right, so we got, looks like a side and an angle here. Anything else you want to tell me? Anything else you want to tell me is true up here? Use your givens. Use your givens. Amy, anything else?
Angle A is congruent to angle C.
Nice job. Good. How do you know that?
Because triangle ABC is equilateral.
Yeah. A lot of people probably would have said AB. Now, let me just back up a second. A lot of you may have said AB congruent to BC because it's equilateral, and that is true. Here's my issue, though. Anybody know how we would prove those triangles congruent? Because it's not side angle side, because that right angle's not in the middle, and it's certainly we're not writing this down. That's just embarrassing. You might just write I'm embarrassing instead of writing that. Okay, that's never a way to prove. Josh, what would it be?
HL.
It would be HL. All right, but I'm not here to review HL with you. All right, I'm here to get the triangles congruent quick so I can show you the new special type of triangle. So we're not going to use, I don't want to use HL, so I am going to go with Amy's suggestion and say angle A is congruent to angle C instead. Yep. Definition of equilateral triangle, not only are the sides congruent, but so are the angles. And now I should have enough information to say the triangles are congruent. What method, though, now? What method would I use? It's not HL anymore, but it's going to be, Gianna, what method do you see up there? With the reflexive side, my right angles, and A and C. You got it. Good work. Good work. Triangle ABD, congruent to triangle CBD. Angle, angle, side, and then we're going to finish this off with AD congruent to DC because of, let it roll off the tongue, CPCTC. I just didn't want to tell you those two are equal, AD and DC. I wanted you to see how it worked. All right, so now you understand that DC and AD are congruent to each other by CPCTC. All right, now let's use all this Let's just use the proof we just completed to answer some of these questions. Find angle A. How many degrees in angle A? Remember, it's equilateral. It's equilateral. How many degrees in angle A?
60.
All right. I'm not calling anybody too. That's fine. It's all right. Why do I have numbers, Josh, right? Just so people can yell out and show off. Yep, 60 degrees. Remember, all three angles are equal. 180 divided by 3 gets me that 60. How about ABD now? Find angle ABD. You got a 60-degree angle, you have a 90-degree angle, and then how about the finisher there? All right, angle ABD. What do you got for me there? ABD, going deep again here. Receive. 30, good work. And now angle ADB, I won't even ask. We already have a right angle there. So welcome to your next and final special right triangle. What was it called on Friday? I had a 45-90 because it was called that because of its angles. Now you have a 30-60-90 we're going to work with today. This is called a 30-60-90 triangle. So just like Friday, can we figure out a pattern with their sides? Can we figure out a pattern? All right. AB is 2. All right. Side AB is 2. Can anybody find side AD? Do not overthink it. Do not overthink it. And even more of a hint, you shouldn't even be picking up your calculator to find AD. It's that, I don't want to say obvious, but don't overthink it. Side AD. And remember what we just said, AD and DC are equal. What are you going to chime in with, Doyle? Yeah, why 1? Why is it a length of 1? What's equilateral mean? All the sides are equal, so all sides are 2. And we just proved by CPCTC, AD and DC are equal. So they're 1 apiece, yep. And now find BD. All right, you can pick up your calculator if you need it here. But find BD. Don't overthink it. Remember the unit we're in. I know 2 sides of a right triangle. How can you find BD? How are we going to find BD? I just yelled at Josh, so that's why nobody's saying a word, right? I get it. What are we using to find side BD? Ooh, Charlie? Yeah, darn right we are, right? 1 squared plus leg squared, B equals 2 squared. And leave it in radical form for me. No decimals. When you have it, what's the length of BD now? What's the length of BD? Let's go, Ian. Square root of 3. Good. All right, square root of 3. All right, here's what I'm going to do now. I don't need this full diagram anymore. Oh, before I move on to the next diagram, everyone agree that this triangle here, BDC, is also a 30-60-90 and would have the same lengths. We all agree? Because what I'm going to do now is detach one of the triangles. And as you can see here, now I only have one of them. I only have one side of it. That's all I need. All right. Based on what we just did now, can you guys find me the remaining 2 sides? All right. Can you find what BC is and what AB will be? All right. Hey, if it helps, I'm not going to leave it up here too long, but if you need to draw on the other side from like the last diagram, you can. All right. What's BC going to be? Remember, it's just half of a equilateral triangle. What's BC going to be down there? 10. Matt, based on last problem, it'll be 2. Good. So that's 2. And now you guys can use Pythagorean theorem to find AB. And then we'll talk about, do we see any patterns in a 30-60-90? Simplest radical form for B, AB. And when you have it, let me know when you have it. AB. Olivia, when you have it. 2 radical 3, yes. Yep. 2 radical 3. All right, here we go. Everyone, we're all right with my values using Pythag. All right, now we have two. We now have two 30, 60, 90 triangles to look at and see if there's a pattern. So under conclusions here, in a 30, 60, 90, we did 45, 45, 90 on Friday. In a 30, 60, 90 triangle, let's see if we can come up with a pattern for the sides. Before we do that, we need to give those sides different names because it can't just be leg, hypotenuse like it was on Friday. All right, and you'll see why. Definitely, we're not changing the name of this side. That side's across from the right angle. That's always our what? Hypotenuse, right? We're not changing that. That's the side across from a right angle and a right triangle is always the hypotenuse. We're not changing that. What we do have to change now, we can't just call those legs because they're not equal anymore. I'm on fire. And they stopped it. John Corleone. Hey. Sure, you got it. Yep, bye-bye. Yeah, we'll see you later. It's been real. It's been good. Hasn't been real good. All right. Video will be up later. All right. Going back to what I was saying. I can't call these just legs because are we all in agreement they're not equal today? Because they're not across from the 45s. So I need to add a little bit more detail to their name. What we're going to do is we're going to call one a shorter leg and the other the longer leg. All right. One's going to be the shorter and one's going to be called the longer. Well, how am I supposed to know which one's which in a problem? You already know. Back in Unit 5, where's the shortest side in a triangle located? Across from what? The smallest angle. Yes, the shortest angle. However you want to put it there. That's fine. You had me going there. Thanks. All right. So where's the shorter leg going to be? Always across from what angle? Which will be what in our case? The 30. So whatever's across from the 30 will be called the shortest leg. Or the shorter leg. Why am I saying shortest? Shorter leg. There's only 2 of them. See, Gabby got me going now. My grammar is awful to begin with. Shorter leg. And then across from the 60 will always be my longer leg. There you go. So 45, 45, we can always say legs because they're equal. We know which ones you're talking about. But now we have to attach shorter and longer. All right, honors kids, here we go. This is why we did this proof. Why we did example 2. Can you come up with your own conclusion on any of those sides? Hey, here's how you find the hypotenuse. Here's how you find the longer leg. Anything. All right, look at the 2 examples we just did. Can anybody give me a rule on how to find any of those sides based on the last 2 triangles we worked with 30, 60, 90? Is there a pattern? And you can say, hey, if you ever want to find this side, this is how you do it. Doyle, go. What do you want to find?
The longer side.
Oh, okay, all right. That's a little tough. That's the tougher one. I like it. So the longer leg can always be found by Doyle.
So the shorter one multiplied by 3.
Yeah, there we go. Shorter leg times, and now here's where I get nervous. Because on Friday, remember we dealt with the radical 2 with the hypotenuse. Now we're dealing with a square root of 3. So make sure you know which one goes with which, right? Radical 3 is 30, 60, 90. Radical 2 is 45, 45, 90. And then, all right, good job, Doyle, good. You took the harder one away. What other side can I find? Look at your 2 triangles. Was there any relationship between any of the other 2 sides? What's up, Matt?
Shorter leg is half that hypotenuse.
Okay, I'm going to go in reverse because that's how I've always written the rule. I'm going to use the hypotenuse first. So reverse it, Matt. Hypotenuse is what?
Double the shorter leg.
2 times the shorter leg. Good work. Yep. And there they are. A little bit more involved than Friday's 45, 45, 90. All right, a little more involved. All right, I just did 2 examples with period 3 and I let them do the rest. So I'll do the same thing with you guys. All right, let's look at my first 30, 60, 90. What is the 12 here? What is the 12? What side is the 12? What do you call that side there? That's my what here? Ian? That's my hypotenuse. So like I did on Friday, and I know some of you guys are way ahead of me, and you don't have to write the rule. I don't expect the rule either. All right. But I write it every time. Hypotenuse says it's 2 times shorter leg, and I'm going to start abbreviating shorter leg SL. Substitute in your value. 12, substitute it in for the hypotenuse, equals 2 times. Now, if you don't like SL, put an X, put a Y, whatever floats your boat. Either way, you can now solve for the shortest leg. What's the shortest leg up here? Matt, shortest leg value? 6, good. Plug it in, 6. And now we're looking for the longer leg. So the longer leg we just found out was shorter leg times the square root of 3. And remember, we don't want decimals, right? So just leave it. Longer leg, 6, square root of 3. All right. Before you guys get ahead of me, can we just talk real quick? And this goes for all of you. Wednesday's quiz, this isn't going to be on fresh in your mind. You got Hills and Sass. You got the 45-45. Let me put you in this scenario Wednesday, and you get me out of this predicament. Let's say I knew that was 6 because I took half of 12. I totally blank on Wednesday's quiz with the longer leg rule. Is there a way I can still find it, though? I gave you 12. You just found 6 on your own. And then I totally blank on the longer leg rule. But can I still find it? Yeah, what can I still use? Pythag. Okay, so keep that in the back of your mind. 2 sides, you need the third, do Pythagorean theorem if you freeze. All right, next up, number 2. What did I give you on number 2? What's that 8 represent up there? What's that 8 represent? Here we go, Gianna, what's that 8? Shorter leg. Awesome position to be in. Because if I give you the shorter leg, you can find any of the other 2 sides. Doesn't matter. All right, you want to start with the hypotenuse, you can find it. Because it's 2 times the shorter leg. So the hypotenuse here, 2 times 8, 16. You could have found the longer leg first if you wanted to. Shorter leg times the square root of 3. So 8 radical 3, or Pythag if you forget. Please finish up through number 6, please. Up through number 6. All right, we're going to do 7 as a class to end it. All right, so up through 6, you can work with, compare your answers with everybody else in your group. I'll put my answers up here. So make sure you're checking your values up here. I got 3 and 4 up here right now. I'll put 5 and 6 up in a second. So here's 3 and 4. We're all good with 3 and 4? All right, let me put 5 and 6 up for you. 5 and 6. We're all good before we get to 7. I know some of you are moving on here. We all good? All right, here's where I need you to be though. That's great that I can give you a single triangle that's got 30, 60, and 90, and you can find all the sides. Great. You know, so can my AB kids. All right, where I need to take you guys in honors to the next level is, what about a diagram that contains a couple 30, 60, 90s, or maybe, and you'll see on your homework tonight, a 30, 60, and a 45, 45, 90 in the same diagram. All right, so here first, number 7, this will be the last time I do this. You should find all the angles first. Okay, whether I ask them or not, find all the angle measurements first so you can decide where your special triangles are. So here we go. I'll go through this quick. Angle DCB, this top angle's got to be 30 because it's 60 and 90 down here. Right next to the 60 is going to be 120. Now, some of you might get stuck after this, finding another angle. Look at triangle ADC. What type of triangle am I working with there? ADC is nothing special, but it is isosceles, right? And what do we know is across with the congruent sides? Congruent angles. So if that's 120, 60 degrees left over, but the two angles are congruent. So we have 30 and 30 here. All right, everybody good? If you want to fill it in here too, you can. DCB 30, CDA buck 20, DCA 30, CAD is 30. Combine the two, you get 60 up here. Do you see any special right triangles here? How many? How many in the diagram do I have? How many? Now, when I say special, 45, 45 or 30, 60, how many do you see in the diagram? We should see 2 of them, right? Triangle CDB, and then the big one, ABC, is 30, 60, 90. All right, ready? I'm going to call on people whether you're with us or not. I'm going to start with that special triangle right there, CDB. What's the 5 in that triangle? What is the 5 in that triangle? Shorter, longer, hypotenuse. What's the 5 in that triangle? What type of side is it, Josh?
Shorter.
Shorter leg, right? Shorter leg. So to go from the shorter to the longer, I multiply by
2.
To go from the shorter to the longer.
Radical 2. Wait, radical 3.
You sure? 3 times the charm?
Yeah.
Multiply by radical 3, yes. So that's 5 radical 3. How do I get to the hypotenuse of this one? Oh, Z, yeah, sure. Multiply by 2. So I get 10. Look what I just did. I didn't even look at what the heck this said. I saw a special right triangle, and I found all the sides. I'll worry about what they ask at the end. All right, I'll worry about it at the end. All right, let me go to the big one now. Triangle ABC is 30, 60, 90. What's the 5 radical 3 now? What's that one? Shorter, longer, the hypotenuse. In triangle ABC, only look at that, or draw it separately. What's 5 radical 3? Shorter, longer, or hypotenuse? Shorter or longer hypotenuse? Josh?
Shorter.
Shorter, good. What do I do to the shorter to get to the longer?
Multiply by radical 3.
Yeah, it's the same question I just asked 30 seconds ago. Yeah, multiply by radical 3, right? So my longer leg, 5 radical 3 times radical 3, I think that's 15. So this should be 15 down here. How do I find the hypotenuse? Multiply it by? What do I do to my shorter leg to get to the hypotenuse? Shoom. Ones. Will, what do I do to the shorter leg to get to the hypotenuse? By 2. Good. So I'm going to take hypotenuse. 5 radical 3 times 2. 10 radical 3. Okay, now I'll go back and solve everything they wanted me for. All right, but I try to fill in the entire diagram first. All right, ready? D, let's see, did I do a good job? DC is 10. CB, 5 radical 3. Oh, whoa! DA? I don't have anything on DA. Because it's not part of a 30, 30, 120. I don't think we've ever talked about the rules for that. I don't think any exist. But how do I get to AD if I can't use any rules? How about using some geometry or some algebra? How can I get to AD? A little help? AD? Gabby, hello? Yeah, well, 10, and I put congruent marks, or that was 15 minus 5. Either way is going to give me a 10. Good. AC, we just found was 10 radical 3, and AB, 15. All right. Find all the sides first, then answer all your questions. All righty, let's get to work.